Welcome back. The purpose of this video is to look at weak base equilibria calculations. Okay, so just as a review, remember this is the general reaction that we have for weak bases. Of course, there is another general reaction out there for weak bases that starts out with the A negative. You're welcome to use either one that you're comfortable with. And then the base ionization constant, Kb, is equal to our products over the original, the equilibrium value of the concentration of the weak base. And then, of course, we have our percent ionization equation, which we'll use as well. So we'll use all three of these in the calculations that we're about to do. So when we look at equilibria calculations for weak bases, we're going to see a lot of similarities that we did with the weak acids, but there are some slight differences. So in this example, they are giving us the pH of a solution. So pH of a solution of household ammonia, the concentration is 0.95 molar, and the pH is 11.612. Determine the Kb value for ammonia from these data. Okay, so remember when we calculated the Ka value for weak acids, we did not need to use the 5% rule, right? Because we're calculating the K value and they have to somehow give us the concentration or the X value for our products. So we always start out with the reaction. So we're going to copy down that weak base reaction where we have B plus liquid water. Okay, yields on the product side, we've got Hb plus the hydroxide ion, OH negative. Okay, and at some point, if you're getting the hang of this, you could just start ignoring the water column entirely and not including it as you write down your ice table. Right, so we get to mark out X through the water column. And we'll also need that Kb expression, knowing that Kb is equal to our products, Hb plus, which is the conjugate weak acid, times the hydroxide ion concentration divided by the weak base concentration. And as before, we know that when we're using that K expression, right, then there we go. When we're using that Kb expression, we have to use the values that come from the equilibrium row. Okay, so filling in what we know, we've got the original concentration of the weak base. So that's 0.950, and then we start out with 0 for the products because we don't have the conjugate acid present starting out, and then minus X for the change and plus X on the product side. Again, all the coefficients are 1, so that's why we can do that. And then 0.950 minus X on the reactant side, and X on the product side. Okay, now in order to solve for Kb, we're going to have to figure out what X is. Okay, now before X came from the pH because the pH told us the hydronium ion concentration. And again, they tell us the pH, right? So pH is equal to 11.612. Now the problem is that if I take the anti-log of that, I'm going to get the hydronium ion concentration, but I don't have hydronium ion as a product when I'm looking at a weak base. And so here's the difference when you're looking at a weak base versus when we had a weak acid. Right now we've got the hydroxide ion concentration that is represented by the value X. And so instead of pH, we're going to have to find the POH. Okay. So remember that POH is going to be equal to 14 minus the pH of the 11.612. Because this is a subtraction step and we assume that 14 to be infinite, then we need to report this out all 3 digits past. And so 14 minus 11.612 should give us 2.388. Okay, so that's POH. If we want to find the hydroxide ion concentration from POH, then we take the anti-log of the POH. And so the hydroxide ion concentration will be equal to 10 to the negative 2.388. Okay, again, 3 decimal places in the POH value means that we want at least 3 sig figs when we calculate that hydroxide ion concentration, but we're going to keep a 4th until we're done. And so the hydroxide ion concentration is equal to 0.00409. And we'll keep a 3 until we're done, subscript it so we know it's not significant. And what does that represent? Well, the whole reason that we did this is because we need to find that value of X. And remember, the hydroxide concentration at equilibrium, right, that's equal to the value of X. And so we've just found what X is. Okay, so now I can plug in for my equilibrium expression. Right, I know the concentration of both of my products are X and X, and so Kb will be equal to X times X divided by the equilibrium expression for my reactant for that weak base, which is 0.950 minus the X value of 0.00493. And so I think you would find out that this is less than 5%. Oh, and I went ahead and plugged that in instead of saying minus X. I'm sorry. So I'll say 0.950 minus X, and then I'll plug in all those values for X, right? So Kb will be equal to 0.004093 squared divided by the 0.950 minus 0.004093. Okay, yes, and so what I was saying is I think that 0.004 will be less than 5%. You could assume that 5% rule and ignore it, but why not include it just to be safe and whenever you're not dealing with the quadratic. And again, you're going to find 3 significant figures in this top number as well as the bottom number even after the subtraction step. And so 3 sig figs in our answer, and we get that Kb equals 1.77 times 10 to the negative 5th. Okay, so just to summarize what we did there. Right, the extra step is that we have to determine the POH. So we're going to have to take 14 minus the pH value first, and then use that to determine the hydroxide ion concentration. And remember that X is representative of the hydroxide ion concentration at equilibrium. And so then once we know that, we can plug it into the Kb expression for all those values of X and solve. Okay, so we're going to do one last problem. This one might take some time because I think we will need to use the quadratic equation. So what is the pH of a 0.082 molar solution of methylamine CH3NH2, and they give us the Ka value? Okay, so quite a bit going on here. If we are calculating the pH, then there is the potential to use that quadratic equation if the 5% rule does not apply. So first step is to always mark out that acid or that base, okay? And in this case, how do we determine if it's an acid or if it's a base? Well, they give us the Ka value of the conjugate acid, right? So we notice that this has 1 less hydrogen, right? It's got 2 hydrogens versus this second one has 3 hydrogens. So this must be my weak base. And then this is the weak acid. Okay, so we're going to mark out that weak base and rewrite it as a B. Mark out that weak acid and rewrite it as a BH, or I'm sorry, an HB plus. Okay, and they're asking about the pH in terms of the weak base. So we want to write the base as our reactant side. So we've got the base plus water, liquid water, yields HB plus the hydroxide ion. Okay, form that ice table. And at a certain point, you may get to where you don't need to use the ice table. You're going to be able to figure out what those equilibrium concentrations are. But they're given the initial concentration of that weak base, right? So that's the 0.0820, and then minus x, and so equilibrium is 0.0820 minus x. Okay, and 0 and 0 plus x, and so we get x and x, right? And again, that Kb expression, just to remind ourselves, that is the concentration of the products over the concentration of the base of the reactant. All right, we are going to attempt to assume that 5% rule and see what happens. So if we're assuming the 5% rule, then that means that 0.0820 minus x is about the same as the original concentration of 0.082. Right, so we're ignoring that minus x. Now if we do that and plug in the values that we know, we cannot plug in for Kb quite yet because they don't give us the Kb value this time. They give us the Ka value, right? But we know how to find Kb from Ka. And just keep in mind that a lot of times when you're dealing with bases, they will often give you the Ka value of the conjugate acid. And so you have to find that Kb value from the equation that we've seen before, where Kw is equal to Ka times Kb. Right? And so Kb will be equal to the value of Kw, 1 times 10 to the negative 14th, divided by the value for Ka that they give us. So that's the 2.3 times 10 to the negative 11th. Okay, so 2 sig figs, so we'll get 2 sig figs here, but if we can, we might keep an extra digit. So let's see, Kb should be equal to 4.35 times 10 to the negative 4th. Okay, keeping the extra digit until the end. So now that we know what Kb is, we can plug that into the expression. So again, going back here, right? 4.35 times 10 to the negative 4th is equal to our two products in terms of x. So we've got x times x, and then divided by the original amount of the reactant, so that's that 0.0820. Okay, so ignoring the quadratic for a moment, we will bring that over and then take the square root. And remember what x gives you, right? So x gives you the hydroxide ion concentration. And so the hydroxide ion concentration is equal to x, which is equal to the square root of the Kb value, 4.35 times 10 to the negative 4th, and then times the 0.0820 times the original concentration of that base. And so the hydroxide ion concentration, or X, and we'll keep out those three significant figures until the end. but that should be equal to 5.97 times 10 to the negative third. And again, units aren't important here, but it is concentration of molarity. So we have got to stop what we're doing. And remember, if you ever need to leave yourself a note, don't forget to check that 5% rule. Okay, so leave yourself a note if you need to, but we have got to take that hydroxide ion concentration and divide by the original concentration of the base and make sure that it is less than 5%. So we'll take that 5.97 times 10 to the negative third that we just calculated, and remember this is our percent ionization, so this is just a check, and divide by the original concentration of 0.082 and times 100%. Okay, so when you do that, you should find that it is 7.3%. All right, so oh no, that assumption does not work, right? Because that 7% is greater than the 5%, which is our cutoff. But just because of that, I would go ahead and finish this out and at least figure out what your pOH is, just so that when you do the quadratic equation, you have a simple check to make sure that you've got the right answer. So they should be very similar, but you will see a slight difference. So since we have the hydroxide ion concentration, I'm going to go ahead and finish this out and calculate the pOH. Now I know ultimately they're asking what is the pH, but we are going to have to calculate the pOH with the quadratic anyways, and so we don't have to go all the way to the pH here. So pOH is equal to the negative log of that 5.97 times 10 to the negative third. Okay, two significant figures, and so we're going to want 2 digits out for this pOH, and we find that it's equal to 2.22. Okay, so we're going to start over using the quadratic, but I'm going to keep a note, excuse me, I'm going to keep a note up here that the pOH should be roughly 2.22. And so at the end, I should have a value pretty close to that. So what I'm going to do is I'm going to go back to this KB expression that I had, and I'm going to add that minus X component right here. Okay, so I'm just going to rewrite that so we have some free space to work with. So that KB value of 4.35 times 10 to the negative fourth is equal to X times X, or X squared, divided by the 0.0820 minus X. Okay, so now I'm going to have to solve the quadratic. So I am going to bring all of this over to the left-hand side, and then that means I'm going to have to distribute the 4.35 times 10 to the negative fourth to both parts. Okay, so I'm going to go ahead and do that in one set. So if I distribute 4.35 times 0.082, that should give me 3.57, keeping 3 significant figures throughout. I know that I need 2 digits at the end for my pOH. Okay, so that kind of helps give me an idea on sig figs. So keeping 3 digits throughout should be enough. So 3.57 times 10 to the negative fifth is that first step. And then minus the 4.35 times 10 to the negative fourth, and that is multiplied times X. And then that is equal to the 2 X's that we left up top, and so that's X squared. Okay, and then we're going to bring everything over to one side. I like to keep the X squared positive, so I'm going to move everything else over to the other side of the equation. So I get X squared plus 4.35 And it might also make it easier, so you could start using the capital E letter. So I'll erase this real quick. Anything to make this easier. We're going to make that 4.35 capital E -4 so that it looks kind of like what's in your calculator. Okay, so that's times x. And then minus the last expression, that's our 3.57, capital E, and then -5. So again, it looks like what you have in your calculator. And that equals 0. So now we can set up that quadratic equation. Remember, x is going to be equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And because we know a, right, a is a value of 1, so let's go ahead and erase those a's because they're just equal to 1. And now we can plug things in. So what I like to do is go ahead and figure out this expression, the square root expression, and then decide if it's greater than or less than the value of b. And so that can help me figure out whether I need to add or subtract that value. Okay, so b is a positive value. Okay, so we hope that since b is positive, well, negative b here would be a negative value. And so this square root function is hopefully larger, and that means that we're going to need to use the positive and not the negative. But let's see that play out. Okay, so we're going to take the square root of b squared minus 4ac, and you'll find that that is equal to roughly 1.196 times 10 raised to the -2nd power. Okay, and that is definitely bigger than the value of b, which is the 4.3 times 10 to the -4th, so much smaller magnitude there. Okay, so we're going to use the positive. So x will be equal to -4.35 times 10 to the -4th, and then add the square root value that we just calculated, which is the 1.196 times 10 to the -2nd. Okay, so add those two values together and divide by 2. And afterwards, you should get that x is equal to, sorry, I'm kind of going in the opposite direction here, going up, but x equals 5.76 times 10 to the -3rd. And keeping in mind that from the last example, we saw that x is equal to your hydroxide ion concentration. Okay, so that x value, remember, is your hydroxide ion concentration, and that we are trying to find the pH, so we can first find the pOH. So pOH equals the negative log of your concentration of the hydroxide ion, 5.76 times 10 to the -3rd. And that comes out to be roughly 2.24. So you can see how similar that value is to 2.22. So it just depends on how accurate that you need to be, right? But this gives us our pOH, and to calculate the pH, the final step, that will be pH equals 14 minus the pOH that you calculated, that 2.24. And so pH is equal to 11.76. Okay, so that's our final answer. That is the pH. We'll just highlight it. Right, that is the final answer that we're looking for, pH of 11.76. And quadratic just depends on whether it's necessary, how accurate that you need to be, but you can see how similar those values are. All right, so that wraps up all the examples with weak acids and weak base equilibria. In the next section, we'll be looking at buffer systems.